Okay, let's unpack this. Imagine you've built this incredibly powerful large language model, right? It can generate text, code, answer questions. It's amazing. But then you realize it's not always doing exactly what you want. Maybe it's too chatty when you need concise, or, too vague when you need detail.
Or maybe it says something unhelpful or even problematic.
Exactly. How do you truly guide it? How do you make it align with your specific needs, your preferences, which might change moment to moment? That's the core challenge we're diving into today.
And it's a huge challenge because what good means for an LLM response is totally fluid. It depends on the user, the task, the context.
Right.
Historically, a really important tool for steering LLMs has been reward models, or RMs. The idea is you show the RM examples of responses you like versus ones you don't.
Okay.
It learns what you implicitly prefer, and then you use that RM to train the main LLM, often through something like reinforcement learning from human feedback, RLHF.
Right. You're essentially teaching the RM to be your tastemaker and then using its feedback, its scores, to shape the LLM. But here's the problem, and it's a big one. Traditional RMs are trained on a fixed data set of preferences. It's like training that tastemaker with only one menu, isn't it? If you suddenly change the cuisine, like instead of preferring helpful general chat, you now need it to prefer concise, highly technical code explanations.
Yeah, that original RM usually isn't much help.
Right.
Exactly. It learned a single, often implicit idea of goodness from that specific data. If your needs shift, you typically have to go back, collect new data for the new preference, and retrain the RM from scratch.
Oof.
And that's incredibly expensive, time-consuming, and honestly, it can introduce biases just based on the quirks of your new data set. It makes these RMs really rigid tools in a world that need flexibility.
So that static nature is a major hurdle. These RMs struggle to generalize to new tasks or adapt when your preferences change, requiring this costly cycle of retraining and data collection. And because they learn from just the outcome, chosen versus rejected without knowing why one was preferred, they can pick up on spurious correlations.
Yeah, absolutely. You see this in benchmarks. They might learn to favor length over accuracy because, I don't know, in the training data, longer responses just happen to be better, even though length wasn't the intended criterion at all.
Okay.
It also makes them kind of a black box. It's hard to interpret why a traditional RM assigned a certain score. You don't get that explicit reasoning.
Okay, so the problem is clear. Traditional RMs are crucial for alignment, but they are rigid, opaque, and kind of brittle. What if, and this is the exciting part, what if we could make the RM itself as flexible as the LLMs they're trying to guide? What if an RM could understand and follow instructions?
That's the core innovation this deep dive is all about. The paper, RewardAnything, Generalizable Principle Following Reward Models, introduces a really interesting paradigm shift. Instead of RMs learning implicit preferences from data pairs, they learn to explicitly follow natural language specifications, what they call principles, that tell them what makes a good response in that specific context.
Principle following. Okay, that sounds a lot like instruction following, which, totally transformed LLMs, letting them handle diverse tasks without needing specific training for each one.
Exactly the same idea, basically.
So the mission here is to really unpack this research. How do they actually build an RM that can follow principles? What are the clever academic approaches that make this work? And what does it mean for how we align AI going forward?
Right.
We're pulling from the paper itself and also a briefing document on RewardAnything.
Yeah, and it's a fundamental change in how you interact with the alignment model. Instead of showing it examples, you give it a natural language rule book for the task at hand.
Okay.
So, for example, instead of showing it hundreds of examples of concise summaries you like, you just give it the principle. Score responses based on how concise they are while still capturing the main points.
And then for a different task, you just swap out the principle. For creative writing, maybe it's score responses based on their originality, vividness, and emotional impact.
Precisely. The goal is to have one RM that can be a flexible evaluation tool across wildly different contexts just by changing that principle.
That's a big shift.
It is. Formally, the task becomes, given a principal P, a prompt Q, and several candidate responses, X100, X may, the principal following RM needs to score or rank these responses based on how well they adhere to P.
Okay.
And the key academic challenge here, the really tricky part, is training an RM that can truly generalize to unseen principles it wasn't explicitly trained on, with all sorts of different levels of detail and complexity.
Right. But if the whole point is generalizing to new principles, how do you even measure that? Traditional RM benchmarks, they only test performance on tasks they might have implicitly seen or are, pretty similar to their training data.
Exactly. That wouldn't work here. This required a new kind of test.
So they had to build something new.
Yep. And this brings us to a significant academic contribution of this work, RABench. They created this benchmark specifically to evaluate generalization to novel principles the model has not been trained on.
Okay, RABench. So how did they build it? What's under the hood?
Well, they started with 50 distinct principles that were explicitly not used during the training of their own model, RewardAnything.
Got it. Kept separate.
Then they gathered prompts from existing benchmarks, things like RewardBench covering diverse areas like chat, math, code, safety. But here's the key. They ignored the original preference labels from those benchmarks.
Why?
Because those labels represented implicit preferences, learned the old way. They needed to evaluate adherence to an explicit principle.
Makes sense. So prompts, yes. Old labels, no. What about the responses?
Right. For each principal prompt pair, they generated responses using 10 different powerful LLMs, think GPT-4 class models, and all those LLMs were instructed to attempt to follow that specific principle.
So you get a range of attempts, good and bad, relative to the principle.
Exactly. A wide range of responses, some adhering well, some poorly, relative to that particular principle. And here's where some of the academic rigor really shines. Creating the ground truth. Evaluating how well an LLM response follows a natural language principle is, well, subjective.
Yeah, I can see that. How did they handle that?
They used 4 powerful LLMs as judges' models, like GPT 4.1 and Claude 3.7 Sonnet. Each judge scored and ranked the candidate responses based only on the given principle.
4 judges, okay. But LLMs aren't perfect, right? They can disagree.
They definitely can, especially on nuanced tasks. So they needed a robust way to synthesize these different judgments into a reliable ground truth. They developed a clever consensus mechanism.
How does that work?
Think of it like finding the strongest agreement across the judges. It uses a dynamic programming algorithm to identify the most reliable partial order, or ranking, of the responses that a significant majority of judges say at least K of them agree on, even if their exact scores or full rankings differ slightly.
Interesting. So it finds the core agreement.
Exactly. This method ensures the ground truth ranking is solid, robust, despite the inherent subjectivity of the task.
And did they check this?
They did. They added a quality assurance step, having human annotators verify these algorithmically determined consensus judgments, and they reported high agreement, 89% agreement with a Cohen's kappa of 0.57, which they note is pretty good given how hard the task is.
That's solid validation. And the scale.
It's impressive, too. Over 1,000 validated principle-specific preference rankings, which they say is equivalent to over 31,000 traditional pairwise comparisons. So RABench provides a really solid, academically sound way to test this new principle-following ability.
Okay, so problem-defined, benchmark built. Now, the model itself, RewardAnything.
Right, the core innovation. This isn't just a standard LLM repurposed. It has a novel architecture designed specifically for this task of principle following.
What's different about it?
Well, it's built to interpret natural language principles at inference time. And importantly, it's a generative RM. It doesn't just spit out a single score number.
Okay.
It produces a structured output that includes its reasoning for the evaluation, the scores it assigns, and a final ranking of the responses. That reasoning part is key for transparency, right? Understanding the why.
Definitely. And how did they train this thing? You mentioned it wasn't just standard fine-tuning.
Correct. The training approach is where we see another significant academic contribution. They didn't use simple supervised fine-tuning, SFT, which often struggles with generalization, especially for complex reasoning tasks like this.
So what do they use?
They used a reinforcement learning approach called Group Relative Policy Optimization, GRPO. Here, the RM itself acts as a policy. It learns to generate the entire structured evaluation output, the reasoning, scores, ranking that best aligns with the principle according to the ground truth.
So it's learning to be a good evaluator through RL.
Essentially, yes. And they specifically adapted this for preference learning, calling it Group Relative Preference Learning, GRPL. It's not just about predicting a single score or a simple pairwise win-loss. It's about learning to produce a complete, high-quality evaluation that reflects the relative quality of all the responses according to the principle.
Relative quality.
Yeah, the source highlights that this focus on relative preferences, understanding the nuances between multiple options, is crucial for generalizing across different principles and scenarios. It's more sophisticated than just saying A is better than B.
Okay, that makes sense. And the reward signal for this RL training must be pretty important then.
Hugely important and quite detailed. This reflects a deep understanding of what makes a good RM output. It compares the RM's generated evaluation output against the ground truth from their training data and gives a reward based on how well they match. It's a weighted sum of 2 main components.
What are they?
First, there's a format reward. This sounds practical, maybe less academic, but it's essential. It rewards the RM for producing well-structured, consistent outputs.
Like what?
Things like including the required reasoning tags, generating valid JSON, having all the necessary keys like scores and best to worst, and critically ensuring the scores it assigns and the final ranking it produces internally match up. This teaches the model how to present its evaluation clearly and correctly.
Right. Usability matters. What's the second part?
Second, and this is where more academic nuance comes in, is the accuracy reward. This measures how well the RM's scores and ranking align with the ground truth based on the principle. And it includes several clever submetrics.
Okay, let's hear them.
For instance, there's a weighted reverse pair penalty. This is smart. It penalizes the RM more severely if it misranks two responses where the true quality difference, according to the principle and the ground truth, was large.
Ah, so getting big mistakes wrong hurts more than small ones.
Exactly. It teaches the RM to prioritize getting the most significant preference distinctions correct. It also includes things like encouraging the RM to use the full range of the scoring scale. Similarly to the ground truth, they call this score distribution matching.
So it doesn't just clump all scores at 3 out of 5, for instance.
Right. And it gives partial credit for getting scores close, even if not exact, which provides a denser learning signal than just right-wrong, plus standard ranking metrics like Kendall's tau for overall ranking agreement.
Wow, that's a pretty sophisticated reward signal. It seems like a key academic insight into how to train an RM not just to predict preference, but to evaluate effectively and match the desired characteristics of a good judge.
Absolutely. This detailed reward structure is crucial for teaching the RM to rank with
This.
They trained RewardAnything using synthetically generated data. They used a different set of 150 principles, ones not found in the RABench test set, along with props from another dataset, Skywork Rewards training set. They generated about 4,000 training examples using a similar LLM judging process as RABench, but without the final human verification step for scale.
Okay, and what about efficiency? Does this principle following approach take longer?
Actually, no. RewardEverything is designed for what they call inference time scaling. It can score and rank all the candidate responses for a given prompt and principle in a single forward pass of the LLM.
A single call. That's impressive.
Yeah, it's a big deal compared to methods that require separate pairwise comparisons between every combination of responses. That approach gets computationally expensive very quickly as the number of candidate responses grows. This single call approach is much more scalable.
Okay, so novel architecture, generative output with reasoning, GPO-GRPL training with a detailed reward function, efficient inference. Let's see how it performed the experimental validation.
Right, this is where we see if these innovations actually pay off. They first tested RewardAnything on the challenging hard split of RABench. Remember, this is where traditional RMs often fail because they implicitly learn biases, like that length over accuracy issue we discussed from their static training data.
And how did RewardAnything go?
It achieved state-of-the-art overall performance on this tricky, biased benchmark. And here's the kicker. It did so simply by being explicitly given a principle that prioritized accuracy over length.
Wow, so you just tell it what's important, focus on accuracy, and it can override those ingrained data biases.
Exactly. You use the principle to directly mitigate known dataset biases. That's a really powerful capability and a direct result of the principle following design.
That really highlights the importance of the principle itself. Did they look into what makes a good principle?
They did, yeah. They explored this in Appendix A of the paper, which offers some great practical and academic insight. Experiments showed that principles with clear priorities, like explicitly stating accuracy only, is more important than maybe length equals accuracy, worked better.
Clear priorities. What else?
And structured rules, especially for multi-objective principles. So instead of just listing objectives like be accurate, be concise, be harmless, providing structured guidance like numbered steps or specific criteria for balancing those objectives yielded much better results.
Interesting. So just listing desired qualities might not be enough, or could even be worse than being vague if the model doesn't know how to train them off. Structure is key.
Precisely. Structured guidance helps the RM understand how to apply complex, multifaceted principles effectively.
Okay, so it aced the bias benchmark by following an explicit principle. What about RABench, the test designed for novel principles?
Right, the core test of generalization. On RABench, RewardAnything performed comparably to powerful general LLMs like GPT 4.1 when tasked with evaluating based on unseen principles.
Comparable to GPT 4.1. That's strong.
It's a crucial validation point. It shows their model actually learned to follow novel principles it wasn't trained on, demonstrating that sought-after strong generalization ability.
And did they dig into why it works? Like which parts of their design were most important? Ablation studies.
Oh, yeah, thorough ablation studies to confirm the impact of their key innovations. If you remove the explicit principle guidance during inference, just give it the prompt and responses without telling it how to judge them, performance collapses.
Okay, so the principle is definitely critical. It's not just guessing.
Not at all. They also confirmed that training the RM on listwise preferences, looking at the whole list of responses at once, was significantly superior to converting that data into just pairwise comparisons, AVSB, AVSC, BVSC, etc.
Why is that better?
It supports the efficiency gains we talked about, but also suggests that seeing the full context of all responses helps the model learn finer-grained distinctions and relative qualities better than isolated pairs.
Makes sense. What about the training method? GRPO versus standard SFT.
That was a major finding. Replacing their GRPO training with standard supervised fine-tuning resulted in the largest performance drop across all the ablation experiments.
The largest drop. Wow.
Yeah, it strongly supports their hypothesis that GRPO, with its focus on generating accurate evaluations and learning relative preferences via that detailed reward signal, is much better at fostering the kind of generalization needed for principle following. SFT, in contrast, tends to just memorize the training data patterns.
So GPO is key for generalization here. Any other key aberrations?
Removing the nuanced relative offense signals from that detail accuracy reward function also hurt performance significantly. This shows that those specific academic components designed to teach relative ranking and score distribution matching really are valuable for performance. And one more, disabling the RM's explicit reasoning process during evaluation also significantly degraded results.
So the reasoning isn't just for show, for transparency. It actually helps the model perform the evaluation.
Exactly. It confirms that the step-by-step reasoning the model generates internally seems to be integral to its ability to apply the principle correctly. It's not just outputting numbers based on some black box calculation. The reasoning process matters.
Okay, so these ablations provide compelling evidence for the necessity of each of RewardAnything's core academic innovations: the explicit principle-following design, the list-wise GRPO-GRPL training that carefully designed reward function focusing on relative accuracy, and the explicit reasoning during inference.
Precisely. They all work together.
Now let's bring this down to earth. How does this paradigm shift actually help in practice? Did they show a real-world alignment example?
They did, and it's a really cool case study demonstrating practical LLM alignment using only principles.
What did they do?
They took a base model, QN38B, and aligned it for complex, nuanced safety behavior. And here's the critical part. They did this using only a natural language principle defining that nuanced safety and just 2,000 diverse prompts.
Only a principle and prompts. No preference data collection, no custom safety RM training.
None. No collecting pairs of good versus bad safety responses. No training a specialized RM just for safety, just the principle and the prompts.
And the principle itself, was it simple?
No, it was designed to be quite complex. It aimed to balance refusing genuinely unsafe queries appropriately, while still being helpful and warm, providing constructive alternatives when possible, and importantly, minimizing incorrect rejections of perfectly safe queries. That's a hard, multi-objective alignment task.
Definitely tricky to balance all that. How did they test it?
They compared the QWin38B model, aligned using RewardAnything and the safety principle, against the original base model, and also against a version aligned using a leading traditional safety RM, Skywork RM, on the same set of prompts, using the same underlying GRPO alignment method for fairness.
And the results. How did the principle-aligned models stack up?
The results were pretty striking. The model aligned using the RewardAnything principle showed improvements. It slightly reduced incorrect rejections of safe prompts compared to the traditional RM. But the big difference was in how it handled unsafe prompts.
How so?
Instead of just blunt refusals, which the traditional RM tended towards, the principle-aligned model gave much more constructive, empathetic responses that still safely navigated the harmful request, aligning better with that complex, nuanced goal.
So better quality refusals, more helpful?
Exactly. And they also saw improvements in overall text quality on a general benchmark, MT-bench, compared to both the original model and the one aligned with the traditional safety RM.
That really demonstrates the power of this principle-following paradigm in action, doesn't it? You can achieve flexible, nuanced steering of an LLM towards complex behaviors just by expressing those behaviors as a natural language principle for the RM to follow.
It drastically lowers the barrier to custom AI alignment. You potentially avoid needing large, domain-specific datasets and custom-trained traditional RMs for every slight variation in desired behavior.
So to sum it all up then, RewardAnything seems to offer a significant leap forward in LLM alignment. It creates reward models that can follow explicit natural language principles, moving past the rigidity and opacity of traditional methods.
Yeah, the core innovations we've explored today are really key. The principle following concept itself as a flexible steering mechanism, the creation of RABench as a rigorous benchmark to actually measure this new generalization ability on novel principles, the novel training approach using GRPO and GRPL, guided by that very detailed reward function specifically designed to teach nuanced evaluation and relative preference.
Right, the academic depth there.
And finally, that practical case study showing how this translates into real-world flexible LLM alignment using just language, no new preference data needed for that specific task.
What this all points to then is a future where we might be able to customize AI assistants to our personal needs and values much more easily. You might not need to be a machine learning expert or collect tons of data.
Right.
You might just be able to tell the AI system or maybe the reward model guiding it, hey, for this task, prioritize creativity and humor. Or for this report, I need factual accuracy and conciseness above all else, all just using plain language.
It makes that kind of fine-grained control seem much more accessible. But, it does raise a fascinating question, though.
Oh.
If we can now specify such complex AI behaviors using natural language principles, and this makes customization much more accessible, what are the most important principles you would want your AI assistant to follow?
That's a good question.
And maybe even more fundamentally, as these systems become more integrated into our lives, who gets to decide what the default core principles for these powerful AI systems should be?
That feels like a really big, important conversation we're just starting to have. A lot to think about there.